Welcome to the AI session. I'm Atif Khan, and I lead Messagepoint's AI research and development initiatives. My team and I are working hard towards redefining CCM and CX use cases by exploring how AI and its various tools and techniques can be leveraged to address the complex challenges that exist in our domain. And then, more importantly, we're also trying to reimagine new potential that AI can potentially bring to this space. We've done some exciting work, and that's basically transformed into our Marcy platform and is being shared with the public through that venue. So the goal today is that I will leverage some of this work to collectively explore with you guys how AI can benefit the CCM domain. Before we get started, let me just quickly walk over how today's session is organized. The main idea is to spend a lot of time discussing CCM and CX use cases that deal and utilize AI. And this is the work that my team has done and the work that we are trying to put forward in our Marcy platform. Before we get there, I think what I would like to do is just basically very quickly go over some of the background material that is required to put everybody on the same footing so that when we have the same definitions of things and we have the same understanding of different terminology, then when we discuss these items later on, that we're all in line. The last piece where I would leave you with is the different challenges that my team faced as we conducted this work and carry out this work. And then the idea being that, in my view, these challenges are not unique to Messagepoint only, but rather anybody getting into this AI CCM CX integration is probably going to come up with the same issues as well. And some of these challenges are actually broader than that space as well. They're just generic challenges. When you consider AI, you need to be able to address them. So I'll spend some time of maybe highlighting some of these challenges that my team faced, and then what potentially we did about them. And then that'll be the overall session. A quick word. Every time you see this icon on a slide, it's an indication that the slide actually is summarizing important content that we've gone over. So if this is your chance to maybe zone in and pay attention and just absorb that material on that particular slide. I promise you that there are no more than 4 or 5 of these. So hopefully throughout this presentation, you see some of these points in time where everything should come together for you. All right, so let's look at some of the basic concepts here. In the context of this session, first thing I would try to do is define what AI means, right? And then for our conversation, I'm going to define AI as this ability for machines to be able to do things that are smart or human-like, and then to be able to do these tasks that human beings are currently doing independently by themselves. And here's some of the examples of these tasks, right? The ability to be able to look at a raw piece of content or data and understand what it is, to be able to parse stuff. I'm looking at a date, I'm looking at an address, not just look at parse the down or low-level characters, but rather the ability to be able to put things together from that low-level character content stream to say, I'm looking at things that we can identify, right? The ability to be able to identify these things leads us to better control, better use cases, leads us to places where we can actually imagine radically new ways of doing things. One of the important things is, like, once you have been able to look at and identify different content pieces from data, the ability to be able to do some sort of computation on that. So similarity is a key thing that we deal with all the time. And content similarity is this ability of content to be to say that 2 content pieces are same or not along any one of these dimensions. Are they same in language? Are they same in what they're saying? Are they same in syntactically? Do they all use the same token, so on and so forth? And then we start from there, and then we also look at additional cognitive tasks like, can I look at an acronym such as BMO and understand that that's not just BMO 3 letters, but it's actually referring to an entity called Bank of Montreal, right? And then they also do cool things like language detection and readability. And some of this is already explored and exposed in the Marcy platform. So again, going back to the AI task, is the ability for machines to be able to do these type of things independently and with minimal guidance from the end user. Okay. Generally speaking, what happens when we try to do this type of workflow, we start out with the raw data. So this is just human beings trying to process content. And then we have to go through a process called ingestion, where we apply or wrangle or apply our mental model of what that data should look like. And we create some sort of schema, right? And then the idea behind that schema is now our guiding principles that tell us how to make sense out of this data. That data, or that let's say process data, when mixed in together with our expert knowledge of the domain, leads to different piece of operational logic where we can now do cool things with it. So we can do we can define what it means to be content to have sentiments. We can define what it means for content to be difficult to read and things like that. Traditionally, the operational logic is all coded. So software pieces have to be written, software components have to be created by developers that now take the ingested data, take the expert knowledge, and then actually write code to create these components. And then we deploy these components in production. Where the AI kicks into this process is as follows. So we're still starting out with raw data. We're still starting out with the domain expertise that exists in that particular domain. However, that process of how we actually come up and compute the end components that get deployed in production is drastically different, right? And this is the piece where this process of I want to make sense out of the data by putting schema on top of it, and I want to write some whole bunch of rules to clean that data, process that data, whatever, and I want to write actually code in Java or in Python or other languages to get to this component that I call sentiment component is all now hidden away from an end user, where an AI-based algorithm can go in and actually create directly from the raw data and the expert knowledge the components that we're looking at, the sentiment components, for example, and the readability component. It's important to understand that these components can actually coexist together as well. So we can actually mix and match hard components that were hard-coded using software and components that were machine generated, and they can all coexist together. Again, so going back to the idea being that machines can actually do this type of task, start out with raw data, start out with the expert knowledge, and give us the sentiment component independently without human beings actually getting involved in writing code for it. Let's assume for a second that we are machines and we're given a cognitive task of differentiating between happy people and sad people. Right? So now this is uncovering how a machine actually would do this and giving us some sort of sense of without having to write code, how this is possible. So we're all machines. Our task is to be able to differentiate between people, and what we do is we go into our population sample set, data set, and then we sample a certain amount of sad people and happy people, right? And that this represents our greater population. Now, before we can make sense out of happy people and sad people, it's important to understand how we can actually measure happiness, right? So in my case, defining two distinct dimensions of happiness. One is income. So the idea being that the more money that you make, the happier you are. And the other one is, let's say, social or online likability. So the more likes you have, the more socially popular you are, the happier you are, right? So on one axis, I can actually measure and plot the social likeness, and the other axis I can actually plot the income. And then what we're defining is that happiness is a function of these two variables, and then people who have high income tend to be happy, and people who have more likes tend to be happy. Now, in a specific case where we are using expert knowledge, what happens is here, this sample set that we've created has known outcomes already. So an expert has gone in and is now telling a machine that these are happy people and these are sad people, and that's all it's doing, right? It's not telling the machine how to figure out like whether we're looking at income or number of likes or other attributes, or which attributes are more effective than the other. It's just giving machine some data points and a known outcome or an expected outcome. And then the idea behind this is the expert knowledge kicking into this process. Now, having known that which ones are the happy people and which ones the sad people, our task as machine is to create some sort of component, function, whatever you want to call it, predictive model that can differentiate between the green ones versus the red ones. So we'll take a very simple example. We'll look at a machine learning model called decision tree, which is very familiar to most human beings, and it's easy to explain, and we've seen some variations of it at some point. So I'll stick with that. So in my case, so again, pretend I'm a machine. In my case, I need to somehow differentiate between happy people and sad people. And so I take a guess. For example, I say anything above this blue line is a measure of happiness, and anything below this blue line is a measure of unhappiness, right? So, or the other way to say it was everybody above the blue line is happy, and everybody under the blue line is not happy. Now, it's a very simple division, and obviously it doesn't work because it has errors, but a couple of things to note here. For a machine to be able to draw a random line or a line guided by certain principles, it's not hard. A machine can go in and try many different combinations really fast. So I can put a line at here. I can maybe move this line up or down a little bit. The idea being that as opposed to human beings trying to make this model, machines can go in and try out a whole bunch of things, and these things are backed by mathematical definitions of what information theory of how do we actually define these lines, right? The second idea is that once I've created a line, I can now actually compute my error rate of that line or my error rate of that decision. So I've made this assumption that everybody above the blue line is happy or are happy, and everybody below the blue line are not happy. Now I can actually go in and count how many mistakes did I make, and based on that count, I understand what my accuracy rate is. All right, so I went in, did the counts, and realized that my first line wasn't good enough. So then what we do is we look at everybody below that threshold that was initially defined and say, okay, how can we improve this threshold? We go in and we create another line, another partition. And then we say everybody to the left of that partition is unhappy, and everybody to the right of that partition is happy, right? And this is now both income and likes are kicking in now. And we realize that at the bottom half of this screen, our partitioning is now improving, is getting really good. So if you follow this tree, at least for the bottom part of that graph, we can predict happy people versus sad people quite accurately. So same thing goes again for the upper half of this notion of this plot, and we can start partitioning the people, happy and unhappy people, by defining additional boundaries, right? So here we're defining an additional boundary. One side of this additional boundary is 100% correct. However, there's still errors on the other side of the left side of this decision boundary. And again, this process goes on till we know that we can actually separate all the happy people and unhappy people from each other by following these partitions that we've created in dividing these two data sets, or dividing these two entities. Then the question becomes, how do I actually use this information? So let's imagine that we get a person that we don't know whether that person is happy or sad, and now we have to do a prediction whether we as machines think this person is happy or sad. The idea is that now the decision tree that we had created, we will go back and pretty much flow through that tree to understand whether we're looking at a happy person or a sad person, or what our classification should be. So in this case, if you notice that we're looking at somebody which is above our initial B boundary of 3, so we basically follow that link, and then we all then say, okay, so where on the A axis this particular record lies, and we follow that link, and then realize that that puts us in a region of known happy people, so we will classify this person as a happy person, right? Congratulations, if you follow this through, as you've basically gone through and creating a machine learning based classifier, and which can now predict happy versus sad people without having to explicitly code, without having to explicitly come up with all the rules, but just by simply providing a known sample of happy and sad people and labels for them, and then the machine can go through it and then make sense out of it. Decision trees are important. However, there are many other algorithms that exist in machine learning and that can potentially help us with similar classification or similar operations, right? So decision trees, we're all quite familiar with. We can also do things like boundary detection. And this is where neural nets, this is where support vector machines come in really, really handy. And then we can also look at from a Bayesian perspective or from a probability perspective, basically make our decision based on what's the probability of something like happening, right? And then combining all those probabilities together. The important message here is that there's various type of different algorithms that exist based on what type of problem that you're trying to solve or what type of problem you want the machine to solve. And we can potentially engineer around this and utilize a number of these. Okay, so again, key takeaways from this first few slides. Machines are learning from raw data. Machines are not going through this step of manual ingestion or manual schema or manual data engineering or data architecture. It's a repeatable process where we can measure how good that process is and how bad that process is. And because it's machine-based, we can actually scale it really, really well. It brings in expert knowledge or the known heuristics that may apply to a specific scenario that we're trying to solve, and allows us to integrate that into the process well. Same overall process that I just described to you, information coming in, machines making sense out of it, and then creating models out of it, is that particular process generalizes really, really well to a whole number of problems that we're solving right now. Okay, so as far as basic concepts are concerned, I think that's all we need to know to understand the material in this presentation. So what we'll do now is jump directly into some of the things that we're doing, how we're actually injecting AI into some of the CCM related use cases. Now, this is my classification of the different types of use cases that exist. So these are use cases that enhance content or allow us to do management of this content in a much more effective fashion, or exert more effective control over how content should be treated and processed, and so on and so forth. And inside each and every one of these high-level classifications, there are specific tasks that we can potentially create machine learning components for. So for example, I think we talked about similarity already. So this is the ability to be able to say, how can I take two different content pieces and train a machine to tell me whether those two content pieces are similar? And then we can define the criteria for similarity as well. I would like to understand pieces that are similar, that are saying the same thing, irrespective of the tokens or the words that they're using, right? And we'll see an example. So what we'll do is, the list is quite large, and I won't get a chance to talk about every one of these items. So what I've done is I've actually picked a few of them that you can actually see in our publicly available Marcy platform, and then we'll just limit our discussion to these. However, the same principles, same way I'm solving these little things apply to solving other aspects of what's on this slide. All right. So again, before we get into similarity, let me just give you a quick definition of what I mean. Again, similarity is the ability to be able to say that two content pieces are same across a whole bunch of linguistic dimensions or content dimensions that I'm interested in. And then I'm also defining this new notion now, which is called consistency or content consistency. And this is the application of similarity to say whether all my content belongs to this same similarity category. So I would like to look at, for example, all content pieces that relate to smoking in my insurance policy. So this is this ability to, now that we can actually measure similarity, can we apply and group things that are similar together and say, are we consistent across all of them? Okay, so to elaborate this use case or elaborate this functionality, let me present you with this example problem or toy problem where we are given 4 sentences. They're all in the same language, and our task is to be able to say which one of these sentences are actually similar to each other. So I'll give you maybe 10 seconds to quickly browse through them and to understand, read them. So it's important because we will be playing with the words and the word constructions. So the idea is that now as a machine, can I create some sort of algorithm and achieve this? A very common way of doing this, or very naive way of doing this, and this actually is what we did initially, is just to count common words, right? So we take 2 sentences and figure out how many words are overlapping between those 2 sentences, and then express that as some sort of ratio. So in the context of S1 and S2, we go back and look at it. It's like, okay, so the entire collection of words, there are 10 words that are used between S1 and S2, and S1 and S2, there's an overlap of 9 of those words out of 10. So I'm going to say, well, they're 90% similar, right? And you won't be wrong. And in fact, there's a well-known algorithm for syntactic string similarity that's called Jacquard similarity or Jacquard index, that's based on this exact notion of overlapping, or how much one set belongs to another set. However, now if you apply the same approach between S1 and S4, you and I can right away understand that S1 and S4 are not similar, right? We understand this concept of negation in our heads as human beings, but machines don't understand that. So if I apply the same naive algorithm to compute similarity between S1 and S4, the machine's going to come back and say, well, guess what? You are still 90% similar. It doesn't understand that the word not actually changes the game, and it's that 90% similarity is now a false positive. Okay. Similarly, if we go back and look at S1 and S3, even though the words that are being used overlap nicely, the meaning of the message is very different. So what S1 is not saying the same thing in S3. So semantically, they're not the same thing, right? So in order to overcome the difficulties that we've seen, what we'll do is, instead of just measuring the number of syntactic tokens, we'll try to measure the distance in the meaning of content, right? And this is where we can draw from subfields within AI, fields such as natural language processing and machine learning, to be able to do this, right? So let's go back to another example. Here I have a set of sentences that are saying either similar things or not similar things. However, they're not using the same tokens or same words, right? So S1 and S2, for example, are saying the same thing, but not using the same words. Challenge being is, had we applied our known algorithm, which counts the number of overlapping words, we would basically come to a conclusion that S1 and S2 are not same. However, if we were to read them, we can then understand that they are same as human beings. Now, how does machine do this? Obviously, we need a richer representation of sentences, which is independent of just the syntactic or the word-based representation. So we need something that can understand the relationships between words as well, right? So these relationships are things like what words are same as other words, what words are opposite of other words, and so on and so forth. Traditionally, there are 2 sources of that we can draw from to be able to make these decisions. One is just a dictionary-based approach or a lexicon-based approach, where we can look at a source such as WordNet and at least for a few languages understand what these relationships are. So given any word, what's the opposite of those words, and what's the same as of that word, right? The other piece that the recent advances in machine learning has brought is called word embeddings. And then word embeddings basically is the mechanism of saying what words are similar given a certain context. So if I'm looking at all Shakespeare novels, what words tend to be similar and occur together in Shakespeare novels. So applying this notion of measuring the distance between the meaning of the words, either by using WordNet or by using word embeddings, if we can somehow get to a conclusion and mathematically tell machines that the phrase "get back to you" is similar to "contact you," and the two words "next week" is very similar to "soon," we can then start to teach machines how S1 and S2, or sentence 1 and sentence 2, are indeed saying the same thing. And just following the same principle, if we can teach the machine that "get back to you" is very similar to "hear from us," and "next week" is also similar to "few weeks," we can again do a similar conclusion where S1 and S3 are very similar. And then if we can understand the word relationships or negation relationships of the words and understand that not changes the polarity of something, and then this notion of negation changes the meaning of content, then we can also make a correct decision when we compare S1 against S4. Okay. Now, given that we now have the ability to be able to look at content regardless or independent of its representation, now we don't have to actually limit ourselves to content in one language. We can apply the exact same principles to actually compute content similarity across content that's expressed in a whole lot of languages, right? So this notion where we were initially just looking at content within one specific language, English, but we were looking at variations on the word constructions, now naturally extends to more languages and variations across word constructions across multiple languages. So how does this magic happen? How do we actually go from one language to multiple languages? So Facebook worked or extended work that came out of Google of word embeddings and came up with their own multilingual embeddings called Muse. And then the idea here is that if I can put my word on an axis in one language, same way we took a happy person and put it on a grid across 2 dimensions, if I can measure my word, for example, cat or car or deep in English, and if I can put it on a plane and then have a measurable way of saying that from the origin, if I go to the right and go to the top by this amount, I land at cat, right? If I can do this, and if I can do this for multiple languages, then I can actually train a deep learning model that takes the 2 planes from 2 different languages and finds me a rotation that puts those things on top of each other, where similar concepts, similar words are very close together in the final word. So again, don't have to understand exactly how this magic is done, but the notion that we can learn things in one language, and independently learn things in another language, and then find these transformations that allows us to say that these things or these words or these constructions across languages share the same space. And then that gives us the ability to measure similarity. So what can we do with similarity, right? So content similarity for us leads directly into content reuse, right? So the idea behind is, as you're actually writing content across multiple touch points, for example, print or email, as you're creating content, machine can actually then measure the similarity behind this content and tell you things like, oh, you've said something like this before, but you've used a different word construction, or you've said something like this before exactly as an exact duplicate. Would you like to reuse that, right? So content similarity leads to reuse, and then if your reuse is correct, that leads to consistency of your content. So same messages are appearing properly across your different touch points, right? this notion of that we can now teach machines the sense of or the meaning of words and meaning of content, and then have them evaluate that for similarity in real time as content is being created, and then provide feedback in real time as content being created, is quite powerful. It's all done independently of human beings sitting down and looking at the final product that somebody's written. It's real time as content is being generated. So because it's real time as content is being generated, we can actually avoid a lot of inconsistencies that can exist by eliminating that at the very source of it. So here's a screenshot of Marcy of our platform, where on the left hand side on the center there's a content editor tool box where you can actually write in content in, and as you're writing this content, what you're getting on the right hand side is this notion of duplicates and similarities of your content. And again, this is machines are processing information in real time and giving you this feedback. And then you're realizing that, oh, by the way, the content that I've just written, there are no exact duplicates of that content. However, I found 3 different things that are very similar to that content. Not only very similar, we can actually quantify what that similarity is, right? So we can actually tell you that there's things that match really, really well, and the things that match maybe not so well, right? And then you can make a decision of whether I would like to replace that content with one of the machine suggested contents, or I would like to keep going and keep working on my own content. The notion around real-time feedback is not just limited to content similarity. Content similarity was just one of the use cases that we looked at. We had talked about additional use cases such as readability, such as sentiment, and then the idea is exactly the same, that as I'm doing editing, as I'm creating content, can I get some real-time feedback around different dimensions of my content? So in this case, the machine comes back and says, by the way, you've told me that you would like to create content that's easy to read, so easy to understand, so between grade 8s and 9 level type of stuff. However, the content that you just created does not meet that criteria, and potentially you can go back and change. It tells you exactly on a sentence by sentence level where that criteria is being violated. And again, very similarly, same applies to sentiments. As soon as you've written something, the machines can go in and on a sentence by sentence level tell you whether something that you're saying falls under the category of negative sentiments and maybe should be rephrased or whatever. This feedback is again in real time. Okay. The other big use case that I want to talk about is universal ingestion. And then the idea behind universal ingestion is that content exists in a diverse formats, right? And for me to be able to understand, or for a machine to be able to understand, we have to actually parse that content given in that format, right? So the machine needs to understand all that different formats that exist across all different contents. This becomes a losing proposition very fast, very soon, right? Because now you need expertise in Word, now you need expertise in PDFs, you need expertise in different content streams, and not just expertise. If you are going to ingest that content properly, you need to know most of the variations and nuances to do a good enough job of content ingestion, right? So it's a hard problem to solve. So we came across the same problem, and the way we addressed this was we will not attempt to cater for individual content types or format types. However, what we'll try to do is if we can look at a piece of content and if we can visually teach machines how to look at it, we will be able to actually parse it. So that's the approach we take. The main AI pieces that are involved here are from computer vision, content or clustering, object clustering, and then language models. So again, the notion is, if I can visually see a piece of paper or page irrespective of what underlying format generated it, I should be able to parse it, right? So here what you're doing is you're looking at a form that is complex. It has a whole bunch of different elements, and then the idea being that can we actually figure out what these little pieces are and then make sense out of them. First thing we have to do is to be able to identify what pieces on this page are important. So an object detection mechanism goes in and basically draws a boundary around everything that it senses that's an interesting piece. So you can't see that in the previous slide, but here it's a zoomed in version of the top of half of those pages, and you see the computer's going in and drawing little boxes around words that it's finding and then characters that it's finding and saying that these are things that I'm interested in. So finding individual items, individual letters, individual words that are of interest on the page is interesting. However, it's not the entire picture, right? What we would like to do is hopefully ask the machine, give me parts of the page that are interesting. That means we need to be able to understand how to group these letters, group these words together to figure out or identify content pieces like paragraphs and sentences that are meaningful to us. The way we would do it is use a clustering algorithm that works very similar to the classification stuff that I showed you earlier on. And then what it does is basically tries to figure out automatically by measuring, in this case, XY coordinate on a page and the distances based on those XY coordinates on the page of each box, and then understanding which boxes are close together to each other, and then grouping them together. So we developed an in-house algorithm to do this. And then on the right-hand side, what you're looking at is a representation of the final output of what our algorithm came back and says, these pieces I think belong together, and these pieces are of interest. And again, this is all done without having to have a human being or an expert to go in and then group things together manually. Machines have parsed the content automatically from an image without having to know what the underlying structure was, and then identify the pieces that are of interest to us. Now, if we can parse the underlying content, obviously we can make use of that information as well, right? But this leads us to truly universal content ingestion, where if we can look at something, we can parse it, and if we can parse it, we can also figure out the interesting pieces on it. So taking the same idea to a step forward, where now what we've done is we know on a given page what things we should focus on. What we don't know is what these things are, or the different types of content that can potentially exist, right? So currently I'm just looking at a set of words. Machines have given me the ability to be able to group these set of words together, but what I would like to be able to do is give some sort of meaning to this set of words. So in this particular case, I've gone in, parsed the content, grouped the content, and now what I would like to do is give it a tag to the content, or give it some sort of label to the content that tells me what this content's all about. So on the top left, I'm looking at a logo, and then I'm looking at an address piece, and so on and so forth. And then the ability for machines to go in and make these decisions or come up with these tags, but just by looking at the content, is the same process that we went over, where we created a classifier between happy and sad people. We take a lot of these samples for example, if you want to do address detection, we take a lot of these samples that look like addresses, we throw them into a machine and say, these are addresses, these are addresses, and by the way, these are not addresses. And then we show the machine a new piece of content and say, what do you think, is this an address or not? And the machine would come back and classify this as an address or not. The idea is that the notion or the concept of an address is important to us. So this process called semantic tagging, and by training machine learning models, we can now actually tag different content pieces that we've parsed. Once you have this ability, you can then ask interesting questions, right? And this leads to from automatic content ingestion to content discovery, right? So you can ask questions like, find me all documents or all content pieces that are in violation of my corporate branding, right? So again, corporate branding could be things like readability. It could be things like where certain things are placed, like brand logos or corporate logos, or it could be as simple as what type of fonts I'm using and things like that, right? You can also ask questions like, find me on content pieces where the address is the obsolete address or is not the same as my current address, right? So again, this is tying in the notion of content similarity now to content discovery as well. And then the what you can do with this, the art of possible is quite large, where you can look at, you can create consistency checkers. You can ask for our content pieces that meet a certain semantic criteria. I'm looking at everybody or every policy that I've ever written and find me all content pieces that talk about smoking, for example, and so on and so forth, right? Now, doing this over one letter, one document is interesting. However, because machines are doing this and because there's a quantifiable way of measuring these things, we can now aggregate these results and present them in a dashboard that you can use to discover the additional things. Why you can apply filters, you can put your mental model and project that onto your data, and then find things that and surface things that are of interest to you. So here you're looking at an output from Marcy's rationalizer dashboard, where we're looking at, for specific type of legal documents, cancellation documents, I would like to be able to understand how many content pieces are duplicates and how many content pieces are similar within certain threshold, and so on and so forth. And all of this becomes available to you because now we can quantify and measure things across different dimensions of content. Okay. So let me maybe end by quickly going over some of the challenges that we faced. And then hopefully these are broader challenges that you should also be looking into if you're interested in augmenting your CCM/CX practices, use cases, implementations with AI. The very main one has to do with data. Right? If you don't have the right data, you can't start with this process. In the machine learning approach to solving this is founded in the fact that you have the data to begin with. The question really you should be asking is, what type of data that I can potentially use to answer my problem, and how much of that data is needed? And those are things that you normally tweak and figure out. And there isn't a magical answer to this question. You'll need your experts to look at your data and go through it, understand its quality, understand its various attributes, and then for the given question that you're trying to answer, perhaps identify certain data sets that the machine can then potentially go through. You could potentially feed all your data set through a machine, but that's an extremely long process, compute-heavy process, and may not lead to results in a timely fashion. So normally this notion of identifying which data sets could be used for the problem that you're trying to solve is important. So I lied to you in the previous slide. The name of the game is not just data, the name of the game is linked data. So by linked data, what I mean is, let's imagine for a quick second that you have a data piece, for example, a tweet that describes certain things. So somebody says, I'm looking forward to attending KDD. And then just taking that tweet and then creating this knowledge graph of what is being said on that tweet, right? So there's a user, and then which name happens to be Michael Jordan. Which Michael Jordan? Is it the basketball player? Is it the Michael Jordan from the machine learning domain? What is KDD? What is KDD England, and things like that, right? So what are the relationships between these things? That's important to understand. If you are looking at starting a machine learning AI practice for your group, and if you're solving your problems by focusing on the image that is on the right hand side, you're doing it wrong, right? The main idea is that you should not be algorithm focused, rather you should be use case focus, and morphing and changing the algorithms that are available and match those algorithms to a specific problem that you're trying to solve, right? So if you happen to spend a lot of time in the math or in the theory, maybe that's the research that is well suited to be done in a different setting altogether, perhaps a partnership with with academia, or bringing in an expert who can just focus on that. It's the engineering piece that is, how do I take that algorithm and then how do I actually implement it so that it could be scaled, it could be applied to the data I have, and it could be tolerant to the data noise and data characteristics that I have. That's the important piece. Okay. If you're lucky enough and you can actually put all this stuff together, the main question you should be asking yourself is this adding value to what I'm trying to answer, what I'm trying to achieve, right? So AI should really be IA, which is intelligence augmentation, right? The fact that you're doing it using an AI hammer shouldn't really matter, as long as you're actually making the process having more information, or making the process smarter so that you can actually do more with that. That's the end goal here. So AI right now happens to be the stepping stone or the tool that we use to get there. However, the real benefit is, can I actually create pieces or create enhancements that can lead to actionable items based on the additional information that I've gained. And then I think lastly, once you've done all this, it's really important to understand and measure, not just understand, but also to be able to measure the quality of this augmentation, right? So if you do all this work and the marginal increase in your accuracy is 2% or 1%, maybe it's not worth it. But without having the ability to measure that is 1% or 2%, you can't answer the question whether AI is actually benefiting you or not. Okay, so in summary, I think AI and CCM, they go hand in hand really, really well, and they're becoming relevant really fast. AI solves a lot of CCM, CX use cases quite effectively, quite nicely, and offers us this plethora of flexibility to reimagine the future together. It's tangible. So I think I talked about a few times that we have a platform called Marcy at Messagepoint that's doing this work, and it's bringing this work to our customers. And then in the end, this whole process gives you a great deal of control over how to create content, how to manage content, and how to actually control your content, right? So it's extremely relevant. Thank you very much.